So, yeah, a quiz next Tuesday. We're off Thursday for Thanksgiving. And what we've done so far is we've talked about 5.1 and 5.2. We learned about exponential functions and then their inverse, logarithm functions. And then, so today I'm going to ease into 5.3. I guess any of this can be on the quiz next week. I don't know if I'll get much further. There's only a couple more sections, but you know, one way to start though, actually I think this was in 5.2. One use of logarithms is, I didn't get to this last time, one use of logarithms is for, to measure earthquakes. I think I might have said it, and maybe you've heard this story. It's called the Richter Scale. They say earthquakes are so intense that they kind of need a scaled down measurement to measure them. And that's what logarithms are. Remember, they're the exponent. Anyway, so this Richter scale is this formula. It's log of, and then this is a little strange here, but it's the intensity of the earthquake over some initial intensity. But then, so that's kind of the formula for the Richter scale. But then what they usually do to you, when they present a problem to you, is they say, wow, that earthquake had an intensity of 10,000 IOs. Which kind of means, well, it was 10,000 times stronger than some very low level intensity that nobody really tells me. But there's some low level original intensity, and then maybe our earthquake was 10,000 times that intensity. Well, anyway, watch how you use this. So then you plug this in for I, and you end up doing the log of 10,000 IO over IO. So guess what happens? Of course, you know algebra by now. You know some algebra by now. The IOs cancel, and you're doing the log of 10,000. But I can see how when it's sort of first presented in a problem without me explaining or somebody helping you a little, it kind of looks confusing. What the hell is IO? They never tell you IO, but you kind of don't need it. Because when you use it, when you plug it into this formula, it cancels out. So now, and by the way, what's the base of this log?
10.
Thank you. When we don't write the base, we all know it's 10. Or maybe one of us knows it's 10. But it's, yeah, we all know it's 10. And anyway, so log base 10 of 10,000 isn't that hard. It's the exponent that you put on 10 in order to get 10,000. The log base 10 of 10,000 is the exponent you put on 10 in order to get 10,000. That's the definition of a logarithm. That was last week. We discussed it. But anyway, you don't need that definition if you have a calculator with a button. You find your log base 10 button and you ask this, and I think the answer is
4.
Is it really? 4. I was about to say 5. I was counting the wrong number of zeros. Right, I screwed up. Yes, 4. That's what it would be. 10 to the 4th is 10,000. Thank you. So, this is a 4.0 earthquake. The book, the actual hard book, has some discussions about how intense that is. 4.0 isn't the worst thing in the world. And we never think about earthquakes here in Florida. We don't have we're not in a seismic active area. So one more time here. There's not much to do here, but one cool thing is, so what if the intensity was 1,000 times stronger? 1,000 times stronger than 10,000 would be well, I think I'd add 10,000. I think I'd add 3 more zeros. I think this is 1,000 times stronger than that one. Well, wait a minute. This earthquake we just had was 10,000 IOs, whatever IO was. It was 10,000 times stronger than IO. This one is 10 million times stronger than IO. It's 1,000 times stronger than that one. Anyway, if I plug it in to the formula, the IOs cancel, and I end up trying to find the log of that number, 10 million. Again, it's the exponent you put on 10 in order to get that number. So he just counts the zeros, 1, 2, 3, 4, 5, 6, 7 zeros, or use your calculator, but the answer is 7. Is that right? I don't know. Again, you might have heard this story before. It's not that difficult. It's just using a formula. You don't have to memorize the formula. You just have to use it in some of the homework. And I may try to put it on a quiz or something. But what's the idea? The idea here is that this earthquake measured 4, this earthquake measured 7. And you might, well, 4 to 7 is not that much different, but the intensity was, what did I try to do here? I tried to make this one 1,000 times more intense than this one. I had added 3 zeros to this problem. This one is 1,000 times more intense. Again, if you remember that the logarithm is the exponent, so it's 3 exponents higher. On a base 10, if you're 3 exponents higher, that's 1,000 times as intense. So, another earthquake that measured 8.0 would be just one number higher on the measuring scale, but that one number higher is 10 times as intense. In this logarithmic scale, it's 10 times as intense. 2 numbers higher is 100 times as intense. 3 numbers higher is 1,000 times as intense. Cool. Another little use of logarithms, and again, I'm sort of at the end of 5.2, so a couple things I never got to, just for fun, just to see the use of a logarithm. They use logarithms for pH. I kind of mentioned these ideas and just never did them. There's this formula. Again, it's log base 10. And this is a little funny. The pH, somehow they measure the hydrogen ion concentration. So that's what this H plus is. It's the hydrogen ion concentration. So again, not a big deal, a lot of big words, a lot of big science behind here, but in a math problem that's presented to you, it's not too difficult. Somebody tells you this usually, and then you plug it in here and take the log of it and try to find the pH of a certain substance. So they measure the hydrogen ion concentration, is a direct relation to the pH, I guess. So one typical problem here would be, where did I see this? I saw this right here. Oh, yeah, right here. Bleach. Bleach is 10 to the negative 13th. Bleach is 10 to the negative 13th hydronium ion, hydrogen ion concentration. Okay, so what's the pH of bleach? Well, let's plug it in the formula and see. So the pH of bleach is negative the log of 10 to the negative 13th. And what's funny again is this is base 10. So 10, just listen to me a second. 10 raised to the what equals 10 to the negative 13th. 10 raised to the what equals 10 to the negative 13th.
Negative 13.
Negative 13. Again, I don't know, there's a lot of ways to think, but log base 10 and a base 10 right here cancel each other out. Anyway, the answer is negative 13. The calculator could help you too.
13,
well, hang on. If the answer is negative 13 with a negative sign in front of it, he's right, makes it positive 13. Right. The answer to the log is negative 13, but there's a negative sign in front of it, makes it positive 13, and that's the pH. And I don't know, how much chemistry you know, and I'm not here to teach you chemistry really, but pH is measured usually from 0 to 14, I think. 7 is the middle, 7 is neutral pH. And when you're on that side, 7 to 14, is that the acid side? This was bleach. Is bleach like an acid? I don't think so. I think they call that the base side. It's less acidic and more basic. I think this is the acid side. Do you guys even know? You don't know? Okay. I think I'm right. Because, well, let me look down here. That was bleach. I mean, bleach might seem acidic, but it's soapy water, ammonia, milk, yeah, that's all toothpaste. Baking soda is 10 to the negative 8. So baking soda is right here at 8. Yeah, that's kind of basic stuff. That's anti-acid. The acid stuff is over on the other side, like sulfuric acid is 10 to the negative 1. Yeah, that's quite acid. Sulfuric acid, which is maybe more acidic than other acids, has 10 to the negative 1 hydronium ion concentrations. Anyway, what's its pH? According to the formula, it's negative log of that number. And when you plug that number in there, the log at base 10 kills the base 10. It's a negative 1. The answer is negative 1. Wait, negative 1 with a negative sign in front of it. Positive 1. The pH is 1. And that's a very low pH, and that's very acidic sulfuric acid. Anyway. Now, how the hell they measure this hydrogen ion concentration? That's interesting. How do they count those little guys? I'm not sure what's going on there. But that's the chemistry. But anyway, logarithms are used a lot to measure certain quantities. Decibel levels of the loudness of sound. The decibel level of sound is also used. But I kind of, well, anyway, so that's cool. Now I'm kind of easing into 5.3, where what I feel like I'm doing now is trying to use logarithms to help me solve exponential equations. So I want to solve exponential equations. So we learned about exponential functions. And I actually previewed this thought last time, that I use these logarithms to help me solve exponential equations. Here's one. I'm making one up here. 45 minus 7e to the negative 3x equals 600 equals negative 654. All right, I just made that up. This is kind of crazy. But what do I want you to do? I want you to solve the equation. Of course, that means solve for x. So, you know, that's algebra. I want to solve for x. Okay, solve for x. Any ideas?
Subtract 45.
Subtract 45. I like that idea. Subtract 45. Okay. That leaves me a negative 7e to the negative 3x equals negative 699. Okay. I think, what should I do next?
Divide by negative 7.
Divide by negative 7. Divide by negative 7. That might not be pretty. That's e to the negative 3x, and that probably doesn't go in evenly, does it? Probably not. You know what I'm going to do then? I'm just going to leave it like that. Rather than, I mean, everybody just went and picked up their calculator, and I kind of wanted you to. I wanted to see if it went in evenly. But anyway, since it doesn't go in evenly, I'm not going to round it yet. I like to round at the end, so I'm just going to leave this as this is positive, by the way, 699 over 7. I'm just going to leave it like that for a while. I like to do my algebra and then pick up my calculator at the end sometimes. So now I want to get to the x, so I want to kill the e. I want to, and we've learned how to do that. I'm sorry for my language. I want to get rid of the e. I want to unexponentiate both sides of this equation somehow. I want to get rid of the e. I want to do the inverse of e. So what do? Natural logarithm. Yeah, a natural logarithm, ln. Good. So here we go. We take the ln of both sides. We take the ln of e to the negative 3x. We take the ln of 699 over 7. Again, I'll wait and pick up my calculator later. On this side, though, the whole point was the ln and the e cancel each other out. You're left with negative 3x down on this line equals this number. It is a number, but to solve for x, I got one more move. Divide by negative 3. So the answer is, x is the natural log of 699 over 7 divided by negative 3. And that's a pure, exact, final answer. But I also might want to know if you can use your calculator correctly and give me a rounded off decimal answer, please. So now I would pick up my calculator. I'd ask for the natural log of this. I'd be real careful. And after I'm finished, I would divide by negative 3. And what's the answer? Might be negative, I don't know.
Negative 1.535.
Thank you. Rounding to 3 places. That is a habit we got. That's the answer, I guess. Yeah, that was kind of easy. Rounding correctly, yeah. You guys okay? Solving for x. You saw, it's you know, a lot of regular old algebra until you expose the base. Once you get the base exposed, you have to get rid of it with a logarithm. And if the base is e, we use a natural logarithm. So watch this problem. What if I have this problem? 10 raised to the 2x equals 782. This time I think you want to get rid of a base 10. If you're wanting to get rid of a base 10, I don't think I'd use a natural log. I think I'd use a regular log, a log base 10. Yeah. So I'm going to use log base 10. LOG and LOG of both sides. By the way, the base was already exposed. All the preliminary steps were already done on this problem. So I'm just going to try to kill the base here. Log base 10 does kill base 10. I'm left with a 2x equals this LOG of 782. Again, I'll pick up my calculator in a minute. To officially solve for x, I should divide by 2 here. So it's the LOG of 782 divided by 2. You're not allowed to take the 2 inside there. That's not what's going on. It's the log of the numerator, then that answer divided by 2. But that's it, right? The steps are easy. So the answer is
1.447.
1.447. Again, just to check to see if you know how to use your calculator. Now you would use your log button, not your ln. I mean, there's 2 different logs. There's a lot of different logs. There's the ln and there's the log, base 10. Any questions? You guys all right? All right, so listen, so there's a theme going on here. We're solving exponential equations. To kill the base, or to get rid of the base, we need a logarithm. All right, and if the base is e, we use natural log. And if the base is 10, we use log base 10. So, all right, so now what about this problem? 7 to the 4x minus 1 equals 827.6. That's not 827.6. That's whatever. 8,276. All right, so what's the theme? Try to solve for x. We have to get rid of the 7, base 7. What do you want to do?
Add 1. I mean, first you're going to...
Actually, no. That negative 1, I threw it up in the exponent there. Yeah. So
I wasn't watching it.
you were listening. Yeah. Okay, sorry. Yeah, so it was up there in the exponent. So I want to get rid of the 7, the base 7. What should I do? Log base 7? Maybe I should do log base 7. Is that what you were thinking? I should have shut up a little longer. I mean, that's the theme, right? When it's base e, let's do a log base e. That's what natural log is. It's a log base e. So natural log, that's why it cancels each other out. They're inverses. When it's base 10, we use log base 10 because it will cancel out the 10. They're inverses of each other. So that if this is the theme, then maybe you're saying if it's base 7, I should use a log base 7. That's very logical and cool. There's a little issue with that, though. I mean, let's do it. Let's do it anyway, but there's an issue. So I'm doing the log base 7 of both sides. I'm doing the log base 7 of both sides. On this side, the log base 7 and the other 7 cancel each other out. And I'm left with 4x minus 1. The exponent just plops down onto that line. They're inverses of each other. They canceled each other out. Over on this side, I have to deal with the log base 7 of 8,276. And one of the issues I have is I don't have a log base 7 button on my calculator. I mean, I don't need a calculator, maybe. I mean, I can keep solving. What would you do next to solve for x?
Subtract 1, or add 1.
You would add 1,
yeah.
and then
divide by 4.
Divide by 4.
And just not finish.
Right. So, right. So I can solve for x, but I just don't know. Yeah. I mean, I can add 1, and I can divide by 4. Here you go. 1 plus this log, and then the whole thing divided by 4. This is a log base 7. I just can't do it because I don't have a button for it. I could guess but I can't do it. I don't have a button for it. Although, I say that, and I've been saying that for many years. You don't have a button for that. The only one you have a button for is natural log and log base 10. Okay, the truth is, after many years of saying that, the years have caught up to me. They've invented calculators that do have, you might have a button for this. I could be lying to you. I'm not sure. Do you know if you have a button? Some calculators now, they have a button where, how does it look? It looks kind of like this. It's a button with a little space here, and so it's saying, dude, you can type in any log you want. You can tell me the base. You can do a log base 2, you can do a log base 7, you can do a log base 8. You have to tell me what the base is. Now wait a minute, I'm saying that, first I'm saying, you can't do this. There's no button on your calculator. And then I'm saying, well, I might be wrong. You might have a button on your calculator. But then I really got a more important point. That ain't the point. The more important point is maybe I can do this without dealing with log base 7. Let's do this problem again. Watch this. All right, now this is an important little idea here. You ready? Follow me here. But in order to follow me, you got to remember the end of last class. At the end of last class, I talked about these properties of logarithms. And I don't know how much you got to practice them yet, but there's these properties of logarithms. There was 3 properties. Listen, real quick though, the last one said that if you have the log of something, and it works for any log, of something with a power on it, what you're allowed to do is take that power and bring it down front. You're allowed to take that power and write it down front. Now that property 3 is kind of, to me, it is the most important one because I can use it to help me solve these problems. Watch this. So in other words, I don't have to go with this theme that if it's base 7, let's use log base 7. I don't have to do that. I can change strategies. I can use, if it's base 7, the truth is I can use any log I want. Because property 3 will allow me to bring this thing down. Let me show you what I mean. So I'm allowed to use any log I want. So if I'm allowed to use any log I want, pick one that's on your calculator. Pick ln or log. I'll pick ln. So I'm picking ln. So I'm taking the ln of both sides. But it isn't, listen, it's a totally different strategy. This time the ln is not canceling anybody. This ln doesn't cancel the 7, and you understand that, I hope. The ln is not the right base. So it doesn't cancel the 7, but it does allow me to bring this down front using property 3 of logarithms. Any log allows you to do that. So I just brought that thing down front. I took the natural log of both sides. It did not cancel the base. It's a different strategy. It allowed me to use property 3 and bring this down front. Now, can you solve for x? You can. It's going to look different than this, maybe. You can solve for x. Right now, see what, I hope you're not confused, but these ln of these numbers, ln of a number is just a number. So this is just a number sitting here. I think I divide by it. Again, I'm not picking up my calculator till later, but this is a number, this is a number. I'm trying to solve for x. I think I'll divide by this number. You could consider distributing it, but I'd rather not. I want to divide by it. So then 4x minus 1 equals this ln of 8276 divided by this ln of 7. So I divided by that number. I'll pick up my calculator later. Can you solve for x? Can you proceed and solve for x? What would you do? Add 1 and divide by 4? Right, right. To whatever the hell this is? Yes, yes. So, so here we go. X is 1 plus this. I don't really need those parentheses I had there. The ln of that over the ln of 1 plus, I added the 1, and now I'm dividing by 4. So that answer looks different. See this answer? And that answer, they look, in a way they look the same. Some parts of it look the same, some parts of it look different. But they're equivalent. If I picked up my calculator and worked this dude out, it should be the same as if I picked up my calculator and worked this dude out. Oh, wait a minute. I can't pick up my calculator and work this dude out. I don't have a damn log base 7 button. That was the whole point. How are you guys doing? I did this problem 2 ways. There's a point. There's an important point here. To solve exponential equations, the first theme was, hey, dude, whatever the base is, use that log to kill that base. Now the strategy just changed. Whatever the base is, the truth is, whatever the base is, maybe you don't have to kill the base. Maybe you can use ln. Just use ln all the time. And use property 3 to bring this exponent down front. But it's a different strategy. We're not canceling the base. We're using property 3 to bring the power down front. Okay, so check this out. So I talked about these properties of logarithms, and this property 3 is useful in some of these problems here. Here's something else that could be considered useful. Because I got this property 3, and I like what I did. I like this, and then I tend not to ever use this. But it's introduced in the book, and I might have assigned it a little. Listen to this. There's this change of base